and I would like to welcome Saikumar Dandla. He will be speaking on the topic Supercharging LLM Interference Performance, and also a little brief about our speaker. He's currently working as an AI research engineer in Amazon. So over to you, sir.
Yeah, it's working now. Yeah. Hi everyone. Hi everyone. So my name is Sai. I was a AI research engineer in Amazon in retail space. So I would like to present one of the most interesting talk regarding LLM and how everyone knows about LLM, and just like ChatGPT is nothing but an LLM. So yeah, how we can do the inferencing and what are the challenges and what are the use cases we have in industry as well as in Amazon. So basically, page attention algorithm, VLLM, those are the two jargons or terms. I will explain by the end. You will also get an idea by the end. So let's please have a look. Supercharging LLM inference performance. So what was this and what we are going to learn about it? I just simplified the entire talk into three components. First one is a problem statement, the challenge. Other one is like implementation as well as the proposed solution. And on top of proposed solution, so proposed solution in this space is like a research work or some algorithm. So, but how was the algorithm was implemented and what kind of frameworks are having the support with respect to that algorithms, okay? So yeah, VLLM Hugging Face. So my talk is more about Hugging Face is a marketplace where every LLM providers used to upload or submit their models into Hugging Face. So with VLLM, we can onboard or make use of any Hugging Face model with the help of this. We can infer any Hugging Face of the model. So let's get started. So the agenda is the era of LLM, how it is growing, and challenges in LLM inference and serving, and inference process of LLM and KV cache. So what was the process? What is inference process and how it used to be? So then the proposed solution, which is page attention and look ahead decoding, and the VLLM introduction and performance benchmarks. So why I was a favorite to VLLM? Why not the other frameworks where we have Hugging Face TGI, NVIDIA's TRT, so and so. So why I was very interested in VLLM? Okay, I mean VLLM is just a framework, but VLLM has the implementation components. Every research used to be published over there. So yeah, I would like to explain few terms, which is throughput, which is nothing but in a specific time how many requests we can process. So requests per second, tokens per second. Inference is nothing but a process by which LLM generates a response based on an input. Latency, which is nothing but delay or the time with respect to, let's say you have a one query. You used to write ChatGPT, you open a ChatGPT, you used to write a query in ChatGPT. So once you write a query and submit the query, then you used to get the response. So once the response got end, then the entire time taken with respect to submitting query till getting the response by the end. So that time frame is called as latency, and time to first token is like a duration. Like once you submitted, so when the first token was generated, that time frame is nothing but time to first token, and the another one is time per output token generation, which is average time how the tokens are generated. So it's like like everyone knows there are lots of LLMs and like even closed source LLMs, open source LLMs, etc. So with respect to ChatGPT, Clade 3, Hugging Face, marketplace models, with programs, so all this. But how these kind of LLMs are served to the clients or the users. Okay, that is more interesting and more important. You can see a graph between closed source versus open source, and more or less now with Llama 3.1, we are close to closed source model performance and benchmark. So which indicates that there is a huge opportunity for open source inferencing and having our own model. Every company can have their own LLM inference or LLM model within their premises or their own servers or their own hardwares. Okay, so the hardware is anyways, it's a GPU, which is a choice based on NVIDIA, AMDs, etc. So now, what are the challenges? So need for more effective way of handling requests. So basically, when you are thinking about LLM, when you are inferencing or serving, basically there are two coins. For a coin, there are two faces, right? So similarly, there are two scenarios. One is either you used to have large number of requests, okay, is the one scenario where it's like in your organization you have large number samples, like just like a AI model, you need to predict large number of samples as a test data set or whatever. That is a one scenario. And another scenario where you are directly interacting with the real time, where you are directly interacting and one question used to send to the model and how quickly you are getting a response. So large amount of request as well as one request. Okay, so serving, which is nothing but how effectively serve a large amount of requests while maximizing cost per query, and inference, which is nothing but latency, how to perform a LLM inference on a single request by maximizing the performance with a minimum latency, which is the time frame, how quickly can get. And the another challenge is, are we really utilizing the GPU memory? So yeah, GPU utilization, GPU maximization, all in so and so. And there are some interesting articles. So before this works, basically APIs are cheaper when comparing with hosting our own inference. But because of these works, now the situation is own inference are cheaper than APIs. So after all the industries are using APIs from OpenAI or Clade or etc. Anthropix, Clade, even Bedrock, etc. But with the help of these frameworks and this technology, we can have our own LLM server within our own inference. So there are few questions or blogs also, like is local LLMs are cheaper than GPT APIs. So this is how so the entire talk is derived on two topics, which is how quickly we can solve with respect to with a minimum time, how many maximum number of requests, how we can process a maximum number of requests, and for a single request, how quickly we can give the response on a single request. So these are the two scenarios. At the same time, how we can utilize the GPU memory effectively. Okay, so yeah, serving the throughput, how effectively serve large amount of LLM request while minimizing cost per query. Okay, so now yeah, so let's look into how was the LLM process, like inference process look like. So everyone used to have a ChatGPT and used to work with ChatGPT, but what is really happening in ChatGPT? So you can see the first box, which is nothing but the cat was is your query. Okay, then how is the generation output token generation used to happen? First token was sleeping is the first token, and second token was peacefully, sleeping peacefully. If you just write the cat was, then you can get okay, sleeping peacefully is a continuous token generation. So now what are the things in this inference process? So basically you can say QKV, like so basically all LLMs are based on transformers. So in transformers, basically three components are there. One is query, key, value. Those are the three vectors which used to be stored and managed entire inference process. But are we really doing very well? That's the point. So this generation happens until we have the maximum length and receive the end of the token. So let's look into some visualized way of understanding it. So the request came, and first one is like your query, and then you can see the decoding, which is nothing but generation. Okay, now you can understand the stages, like is Apple is apple a fruit is your prompt, and then the decoding phase, which is the generation phase, token phase, yes, it is. Okay, so the prompt is nothing but a prompt phase, and the yes, it is a decoding phase or token generation phase. Okay, so now time to first token, you can see the prompt, and the first yes is a time to first token, and token per output time, like time per output token. So these are the things which is happen in LLM. But more importantly, are we effectively using memory? Okay, that's because we are storing KV cache, because every token, the query as well as the output needs to be stored effectively. So how that is happening? So you can see basically we are storing in a memory space. So KV cache is dynamically grows, okay, and it grows until the maximum size or special token called end of the token. So in decoder phase, what happens? A decoder always try to compute the attention and generate a token and use to update the KV cache. And without cache and with cache, you can see the difference. With cache, we can effectively do the computation. So we are in need of saving or storing the KV cache in our memory. But the problem is, are we really doing in a right direction? That's the problem. So how we can get a high throughput, which is nothing but within a timestamp or multi-processing in a concurrent time, how we can process multiple prompts, all of those. Okay. So the problem here is how much memory is taken. So you can see basically these are the model parameter memory and KV cache 30% and others, and you can see the existing systems versus VLLMs, and you can see the memory, the continuous memory is allocated and the memory was not showed because continuous memory, if you are aware of operating systems concept, in operating system we used to have for one process we used to have a continuous memory allocation. Okay, when the memory was continuous memory allocated, then it is dedicated for the process A or process B, whatever. It is not going to be shared for the other process. So there is no memory sharing. So it's like a memory fragmentation and sharing in OS. So what is this? So when you see, this is how you can see entire how it is. So the KV cache memory and then current tokens, future tokens, internal fragmentation, external fragmentation. Why it is happened? Because we are giving a reservation. We are saying, hey, you are going to have a maximum token of 100. So always give 100 dedicated continuous tokens. So but in internal fragmentation, unknown output length. Are you really using 100 tokens or 100 sequence? No. Because we are not sure, or most of the time we are not using effectively. This reservation, unused future tokens, and these reservations are making the model to underutilize 38% of memory. So you can see the usage, memory wastages. So this is how it is. Let's install a VLLM and let's solve this problem with a VLLM, and then I will explain how the VLLM is solving. So you can see a pip install VLLM. I'm just doing a pip install VLLM. And here I'm going to do an inference. So just an inference package, importing libraries, then loading one of my data set, a prompt data set and queries data set. So after that data set, I used to choose my model. So I'm taking a Microsoft model, the Py3 model, and some parameters. And then I used to load, with the help of VLLM, I used to create an instance and I used to load the model. Okay. Then I used to, yeah. So then I used to do the generation for my fifth. So here in this use case, like I said, I was more interested how can I handle large amount of requests. Let's say in this case I taken a 5K request to show a complete demo. I taken a 5,000 prompts or queries. So for 5,000 prompts or queries, how effectively I can generate within how much time, within what time I can generate responses for 5K prompts. So that's what we are going to see here. So this code is shared in a work doc. So I will share every details, entire the talk details in my work doc by the end. So don't worry about it. And you can see I just taken a LLM class as an instant, and then I'm going to call the generate function. So now it will generate. You can see it will generate, like I just created some timer to compute how much time it is taking. You can see there are few functions, which is generator function, and you can see the outputs. And you can see that 5K prompts. So how much time it's going to take? It's take very less. So that's where I'm playing here. So you can see the time, and there are some warnings just because of the maximum length with respect to model, which is exceeding. But yeah, so let's look into it. So by the way, I'm using NVIDIA's P4 mission, which is A100 mission basically for the demo. So 94. Yeah, you can see, right? So within a 44 seconds, this model was able to process 5K prompts. You can understand how much minimal cost per query we are able to getting. So in AWS or whatever the services, if you are looking into services, most of the services used to pay are bill based on hours, number of hours you are using, right? So then if you are using a 5K prompts, generating a responses for 5K prompts in 44 seconds, just think about it, how quick it is. And I will give a benchmarks, performance benchmarks, mentioning that is it this 5K is really a big number comparing with the others. Why I'm saying 5K, I mean this 44 is really good. In reality for the other, what is the expected time for the others as well? Okay. So now, yeah, so now let's look into the model. So here how this has happened. What was the proposed solution or the implementation was there to happen this? Okay, the proposed solution was effective memory management inspired by virtual memory and paging technique. So it's pretty simple because it's a clear and a genius idea in my opinion, which is simple idea and like general idea. Everyone knows about it, but these guys like PhD from Berkeley students implemented and explored and published a paper out of it. So here a simple idea called in memory. So if you see this, so yeah, in a simple way, you know operating system, you know process, you know virtual memory, you know paging concepts. So instead of giving a continuous space, so we used to have a virtual memory and we used to have a paging concept. In paging, so based on a request, based on a process, it creates a pages. There is a paging scheduler and the scheduler is responsible to create the pages based on a process required. So it creates a pages based on a required. So page 1, page 2, page 3, physical memory basically. Instead of giving a dedicated memory, we are creating on demand or as required. Okay, so the same concept, which is exactly same. Here few differences, which is the KV cache. Here we need to have the memory for computation or storing, right? So here we need to store our KV cache effectively into the memory. So that's the reason. Okay, we have this request A and request B. So we are having this similarly like a physical memory. We are having a token block as a just like a page. We have a token block, and then we are storing our KV cache. So how this is happening? This is purely a virtual memory paging concept in terms of LLM inferencing and adopting in LLM. So let's look into what is token block. A token block is nothing but a fixed size of contiguous chunk of memory that can store the token states or tokens, the generated tokens, the query tokens and generated tokens in a left to right manner. So you can see that this is a fixed block, which is maybe a 16 or 32 based on our needed. So you can see how a prompt, which is artificial intelligence, is stored here in a left to right direction. Now let's look into one walkthrough how it really makes sense. Now we are effectively handling KV cache. Then how the page attention is going to take a place here. So page attention is nothing but an attention algorithm that allows for storing continuous keys and values, continuous. So I'm not disturbing the keys and values position. I'm still keeping the continuous manner which the keys and values are required, but I'm storing in a non-continuous memory space in that token block. Okay, so you can see that this is the query and this is the KV cache. Now this query, for this query, so we are storing in the dimensions. I have one good example. So physical block and yeah, so you can see this is my request, this is my prompt. Alan Turing is a computer scientist. Then this is my prompt. So if I'm going to give my prompt, so it generates the next tokens and next output. Okay, so this is a physical token block or KV cache. So this is a logical token block. So how it's going to be happen? I'm just keep visualizing it. You can get an idea easily. So and is a new token got generated here, and it's stored in a physical token block, and now it is taken to the from logical token block to physical token block with the help of block table. So you can see. So now, yeah. So now here by the end, and mathematician renowned is in a logical block to physical block. So it stored and mathematician. After that, then again it allocated on demand to the next block based on in that entire token block. So this is how it stores. Instead of giving a continuous space, it gives based on this in a simple dimension, 2 dimension to 1 dimension. 1 dimension to 2 dimension in a simple understanding. Okay. So this is how it is implemented as a page attention. So now let's look into the serving multiple requests. This is very important. This is helping the throughput, high throughput. instead of serving one request at a time, so how we can serve multiple by keeping the same space. So you can see this is request A and this is request B. So both requests are parallelly served the KV cache within the same block. You can see the yellow boxes for the request A and the green boxes for the request B. So this is all about, so now are we really solve the problem? Yes, we are able to solve the problem. So the internal fragmentation is very limited. It's just how much you are fix the size of the token, okay? Size of the block size. And there is no external fragmentation because we are using the virtual memory and paging concept where we are allocating based on a demand only. So you can see from 20% to 96% utilization. So previously it is 20%, 20 to 30%. Now it is 96% because we are using if needed in a simple way and very limited or minimal wastage of internal fragmentation. So yeah, this all about it, and what we achieved, it is completely reduced the memory fragmentation, enabling sharing, 4x serving throughput, increase 4x in terms of 4x serving throughput, and it has multiple techniques of sampling, long sequence, and it reduces the memory fragmentation with the paging concept, and it enables memory sharing because of having token blocks shared in a multiple ways. Okay, in a single token block, we can store multiple requests. Okay, so inference. Now let's look into the inference. So far it's clear, right? So what we are doing, we are so we have a problem, and we have a solution with respect to, which is inspired by virtual memory and paging concepts. It's very simple, but it is very effective in terms of serving LLM throughput. So now let's look into a latency inference part. How to perform LLM inference on a single request while maximizing performance. So now, basically this is very hard because even you request one request or few, still you need to complete the entire iteration. You need to enable all the resources. You need to compute complete resources even for a one request also. But how can we do that? And what is the way? Even if it is only one request, still we need to do the entire steps, entire computation for the single request where there is no parallelization and nothing. So now what we can do as a best? So yeah, yes, we can do the best, and I have one beautiful visualization. You can get an idea what we are doing. This is the existing and this is the proposed. It's already done. Here you can see this is a prompt. User given that which methods did separate some question with methods or something. They given a question. So for the question, the LLM is generating the response. You can see the response generated from left side to right side. There is a huge difference. It's nearly 2x. So how we achieved? Then we have a look ahead decoding. I will explain what is it, and what was the intuition behind. So this is how we achieved a inference. Even a single request, how quickly we can able to generate a response. Okay, let's look into some code walkthrough. So I created one prototype. So where I created a real-time application, I created one LLM server, and I created one client application. So now you can see. So I already installed a vLLM, and there is a command called vLLM serve and the model name and D type and the API key because I'm creating as a LLM server. So then I used to connect. So you can see that, right? So just I'm running this. So you can see first. So once I execute the code, it creates a local server. Okay. So for the local server, I just created a client application as a chat assistant with a Gradio, so connecting to the client. Okay. Now you can see this. Yeah. So here it's very easy. Like you can see, hello, how are you? So this is a client application which is connecting or requesting to the LLM server which we already hosted. So in this client application, like I said, how quickly I'm going to give a response for hello, how are you? If I just turn on, within a second it gives a response. Yes, you can see that. Even for the second question, let's say you can see from the server side, you can able to see there is a 200 and OK, which is the server side response. Let's ask one more question, which is what weather like today. So you can see the response generated in a milliseconds basically. So even this response is very minimal. Even if you ask a lengthy question or very detailed prompt or question, still it generates a response. Even I can guarantee that 1x to 2x based on my observations as well with the existing system with look-ahead decoding. Because we have the other techniques called auto-regression method with many techniques are there, but this is very interesting and very advanced. And this 2 months back only this was introduced or published from Stanford PhD guy. So it's really improved a lot in real-time applications. So now you can see nowadays even ChatGPT and Clade used to respond very quickly, very minimal time. Like if you ask it, even anyone used Haiku LLM, I mean like Clade Haiku. So you used to see that the response, the time of the response, right? Literally that is achieved with the help of this look-ahead decoding. So that's the difference. Like, so if you ask the question, it keep executing very fastly. So yeah, that's all about. But let's understand what is behind, what was the solution, and how it is, what it is. Okay. So look ahead decoding. So look ahead, like look ahead decoding is nothing but there are two components. One is look ahead and verification. Very simple. Here also very simple. So everyone knows about Jacobi methods. In our 10 plus 2, everyone knows about Jacobi methods and Jacobi decoding, right? Like, let's say you have a x1 plus x2 plus x3 is equal to 5. Again, one more equation, x1 plus x2 plus x3 is equal to 10. x1 plus x2 plus x3 is equal to some 12. So these are the three equations are there. Then you need to compute and figure out what is x1, what is x2, what is x3, right? So then first you used to assume some values as 0, 0, 0 or something as a random. Then you used to compute those three equations and you used to find what was x1, what is x2, what is x3 after computation. So this is how a basic Jacobi decoding works. So now instead of taking a linear fashion, this Jacobi decoding help us to solve this problem in a non-linear fashion. So which is again in a simple way, there are two components, two branches. First branch is look ahead. Think like a two actors, actors in a way, not the real act, I mean the movie actors. Two actors are there. One actor's responsibility is to predict the future. Okay, so future token generation. Let's say the next 10 tokens are this. I'm saying these are the next tokens for the 10 generations. That is look ahead. Look ahead, the name indicates that it looks ahead. What are the future tokens it could be. Now this verification branch, which is another actor is responsibility to validate. Hey, you predicted this 10. On this 10, what are the tokens are really going to be the real tokens. So the problem here is in inference phase, you used to see every time there is only one token got generated. So we can able to solve the problem. Instead of generating one token, if we generate 2 tokens, 3 tokens, 4 tokens, then we solve the problem. That's the concept, simple. So now this look ahead used to look for 10 tokens. This verification branch used to say these 2 tokens are correct. From this 10, these 2 tokens are correct. So now irrespective, like previously it is a 1 token decoding at a time converted to 2 token decoding, and everyone knows about n-gram technique. So they implemented n-gram technique. The 2 can be 3, 4, any number. Okay. So let's look into this one small visualization. Sorry. Okay, it's taking. Yeah, you can see this is your prompt. Ellen Turing is your prompt or query, and this is the guesses. These yellow boxes are guesses, and this green box are accepted tokens. First it guesses, and then it's validate. It used to check, and it used to compute, and then it used to verify. If it is okay, then only picked up. From guesses, A is not okay, then don't take it. Then go to the next. So likewise it takes. So now, so from this, so then we constructed, instead of taking 1, then how can we take n grams out of it? So Ellen Turing, so yeah, you can see who is a future token generation. Now we taken 2 grams, 2 pool grams, and so now matching 2 grams start with is. So wherever is there in this, so is there here. So now take is A. So now again after A, then see is there any new 2 grams which are start with A. If it is no, then okay, done. Again, go and guess it. It's like an iterative process. First step is guess, second step is verify, third step is accept. Then iterate. Okay, so here you can see. First step is look ahead branch used to see the future tokens. Verification branch used to verify and collect the n-grams based on it can be 3, 4, whatever the number. And once it is done, then again update your look ahead branch. It's like that. So with this we are able to reduce 2x times of latency on manual evaluation dataset and 1.5x on a real time chat applications, and 1.9 on a detection in a mathematics problems. So yeah, this is all about, and this VLM supports even any model on Hugging Face. I given this demo where you can see I just make use onboarded multiple models and generated.
Yeah,
Yeah,
I'm so sorry, but we have to cut off.
Yeah.
It's time.
Yeah, just like I have 1 minute. I can say over here.
It's
just
already 11:30. I'm so sorry.
Yeah. Okay, just give 1 minute. I just complete it. So yeah, this VLLM, just you can see what are the advantages. That's all about performance benchmarks. Yeah, that's all about.